Okay. Okay. So thank you. First of all, thank you, Dima, for inviting me to give these lectures, and thank you all for coming. Yeah, it's a great pleasure to be lecturing in this. So the topic I chose is this tridiagonal random matrices. So it's a specific, I mean, one approach to some of the questions in random matrix theory. So let me say straight away that if there are any experts, maybe they will not get as much out of it. So I aimed it to be, so I assume that most of the people are graduate students. So I kind of, it's a basic course. So I start from the beginning, and we'll see how much I can do in 4 lectures. Okay, so let me start right away. So yeah, so random matrix is a huge field. So here we can take, okay, I have pre-written some things. Most of it I will write here. And also please feel free to ask questions and so on. So of course, we can have questions at the end, but if I'm not clear, I'll be happy to be interrupted at any time, okay? So what is the objective? So we can take as our goal this beta log gas. So one can take as the goal the understanding of this beta log gas. What is the beta log gas in 1 dimension? So it is n particles, lambda 1, lambda 2, lambda n, having density which is given like this. It is given in this form: e to the minus beta n squared times an energy function h of lambda, which I have written here, and h of lambda is given in this form. So let me explain this. So more or less the entire course is about understanding this kind of an object. So what is this? So first of all, this kind of specification where we will specify the probability density. So this is a probability density, of course, on, so this is a probability density on Rn. Okay, so what is the, so this way of specifying is very common in statistical mechanics. So we know that when you have a configuration, you specify its density as e to the minus some energy. And along with that, we usually put this parameter beta, which is just a positive number. Okay. Okay, I see 1 second. So something strange that happened here, which is, oh, okay, so this is the density that we are working with, and here the energy is given in this way. So the way I have written it is scaled already, beta n squared. So for reasons which I'll explain later, but the energy looks like this. It is h of lambda, which is the sum of, it consists of 2 parts. One is the sum of the individual energies, summation v of lambda k, and the second part has to do with pairwise interactions, lambda I and lambda j over all pairs I and j. Okay, what does this look like? For a moment, if you assume that the second thing did not exist, okay, so then what would we have? We would simply have e to the minus n times, okay, n square beta times summation v of lambda k, which is just n independent random variables with density e to the minus beta n square v of x, right? So that we understand. But here there is an interaction coming from the second term, which is that lambda, the energy here, when lambda I and lambda j are very close, the logarithm is going to negative infinity, and then there is a minus here, so the energy goes up. So overall, the way the probability density is defined, lower energy configurations are preferred. And when lambda I, lambda 1 and lambda 2, let us say, come very close, this energy goes up, so that makes it unlikely. So this second term, this introduces repulsion.
It's 7 o'clock.
So this second term introduces repulsion, which is also seen from this form. So in this case, you can see it as e to the minus beta n times summation v lambda k times this term where you have this Vandermonde raised to the power beta. Okay, so this tells you that if lambda 1 and lambda 2 come close, then the density becomes 0, so they repel. In other words, such configurations where 2 particles are very close are unlikely. So this way, so we get this interacting system of particles, and the whole goal is to understand this. So what is there to understand? What are the questions? What do we want to know? Okay, so the questions are like what you do with independent random variables. So some of the questions, so let me say, what do we want to know about them? So one of them is, where are the particles? Okay. So where are they? I mean, how far? I mean, on the real line, we know there is this probability density, but where are the particles actually? So, for example, how big is lambda n, or how small is lambda 1? Okay, so that is the range. Lambda 1 up to lambda n is the range. So what is the max and min? One can ask questions about that. Where are they and how are they distributed, etc. Once you know where they are, then you can ask final questions, how they are distributed there, and so on. Also, you can ask about the overall distribution of particles. So what is happening is actually, so from this density, as I explained, so if you just had n independent random variables, that we understand. But here, this repulsion tries to push them apart. Okay, so if we did not have this minus v of lambda k term, suppose we had only this term, this log that one. So then you see that density is like this. I mean, that's not a density. The thing is they push each other so much that they fly away to minus infinity to plus infinity. It is this first term which keeps them together. So there is a trade-off between the first term and the second term. First term is trying to keep them together because, okay, first of all, you have to assume what is this v. I did not say what v is, so let me write that. So v is a function from r to r, and you have to assume that it goes sufficiently at infinity so that this defines a, so think of v something like this. Okay, a prime example, in fact, most of the lecture I'm going to work with is the quadratic one. Okay, so this is the special case with which we are going to work for most of the talk. But we'll also mention other things. So V should be thought of as, so for example, what else other than the quadratic? Anything like V of x equal to an even polynomial. You can take x to the power 2p. It has to go to infinity, both at minus infinity and plus infinity if you want. So that's why if you take a polynomial, it has to be an even polynomial. And let us say anything like this is good. Okay, so that's already a lot of potential. So this V is called a potential, and one would like to understand the role of that. But in all these cases, that e to the minus v term tries to keep the particles, push it away from minus infinity infinity. The repulsion tries to push them away, and the trade-off is what we need to understand. So that is what here I mean by overall distribution of particles. Okay, so there are many questions in this, and also you can ask about what are the gaps between particles. Okay, so gaps. So let's say lambda n is the largest and lambda n minus 1. How big is that gap? Or you may go to somewhere in the middle of the lambda n by 2 and lambda n by 2 minus 1. Two particles in the center of the thing. So how do they look? So the particles are distributed on the line, and just these are all the questions sort of we want to understand here. Okay, so okay, I should have brought some simulations to show, but I did not. So anyway, so here it is. So these are all the questions that sort of questions that we want to ask. Now, where is random matrix in all this? So there is no, as of now, not yet. So how are we going to study this? One option is, okay, so you have the joint density. Why not study it? I mean, it looks like a very explicit joint density. Why can't we study it directly? So it is possible. Some things can be done directly from the density. So what are the approaches to trying? So one is maybe directly from the density. It's certainly an option. We have an explicit density, and why can't we work with it? The problem is it's the n is it's always all these as okay. I of course I should say it. All these questions are we are interested in as n goes to infinity in a when you have a large number of particles. Okay, so that's what we are interested in. So you might want to study it, but the problem is, so this is a joint density of very many particles. Unless you can integrate out things, it's not always easy how to work with it. For example, if you want to know, one of the most basic things is on the real line, I take an interval and I ask what's the expected number of particles that I see here. So here is an interval I, and what is the expected number of particles I see here, or the variance of that. So it's not, so expected number of particles you would be able to find if you could integrate out, if you could find the density of lambda 1, of lambda 2, lambda n, or you just make them exchangeable and you find a typical randomly chosen, so you pick a lambda I at random, and if you could, that's one particle out of all this, if you could find the density of that, then you could answer what is the expected number of particles here. So for example, what is this? This is the density of lambda, probability that lambda 1 belongs to this, plus probability lambda 1, lambda 2 belongs to this, plus probability lambda 3 belongs to this, and so on. So if you could find these univariate probabilities, you would be able to answer such questions. But that requires you to integrate out all the other variables in this high dimensional joint density. And that is not so clear how you can do that. In fact, there are no formulas except in special cases. So that is, it does happen in special cases. So it is a little bit is possible. Okay, actually a lot is possible, but this will not be the subject of my talk. So I will mention once or twice what one can do directly with the density, but mostly it will be to sort of speak ill of this method, rather that is complicated or something like that. Although I must say that many things that we will say have been also approached directly from the density. There are methods of mass transportation and other things by which people have approached it. I will mention that later. But so a little is possible, but a lot is possible, especially from this naive approach, which I said, for beta equal to 2. So if beta is 2, nothing looks special in this density. When you see the density, beta equals 2 doesn't look anything special, but there is a little bit that is special there, and that you see in this term, right? So in this term that I have highlighted here, so this one, when beta is an even integer, at least that's a polynomial. It is, there is an absolute value there, which is actually a pain to some extent. But you have, if beta is an even power, that becomes a polynomial. And of all of that, the simplest is beta equals 2. So in some sense, beta equals 2 is special. But there is something very special about beta equal to 2, which makes this actually workable directly from the density because of what is called, there is a determinant structure. We will not be talking about this actually. I am just going the words there, but we will not be talking about this determinantal structure at all. But that is the first approach. In fact, that was how this was studied. It was all studied for beta equal to 2. The simplest is beta equal to 2 and quadratic, and then people studied it. And then people were able to do beta equal to 2 and general B. There are some things called Riemann-Hilbert methods, again, things which we will not talk about, which made a lot of progress in this field. But those methods fail for general beta. They work for very special beta, such as beta is 2, also beta equals 1, but in general, they don't help. So the determinant structure, I am not saying what it is, but it allows you to integrate out and get this explicit marginal densities. That is what it does. So what else can one do? Something that has been known for now, what, 60, 70 years now is, again, in the special case of beta equal to 2, there is a realization and V of x equal to, no, let's say V of x equal to x square. When beta equal to 2, Vx equal to x square, it turns out that lambda, log gas is actually lambda 1 up to lambda n, have the same distribution as eigenvalues of a certain random matrix. What is that random matrix? It is called GUE n random matrix. Let me define that. So it is just GUE random matrix is this matrix, which is an n cross n Hermitian matrix, which is defined as, let me write it as B plus B star over square root 2. Okay, so B plus where Bij are IID complex Gaussians. IID standard complex Gaussians, which means that the real and imaginary parts have, well, the density on the complex plane is e to the minus mod z squared over pi. That's what standard complex Gaussian is. By standard complex Gaussian, I mean this density. And if Bij's have this density, then you form this Hermitian matrix by adding to it its conjugate transpose. Then the eigenvalues of A have the density, which is exactly, one can work out that it is exactly this density that we have asked, with the special case Vx equal to x square, and maybe it is x square by 2. It doesn't matter too much. Possibly, yeah, it's probably x square by 2. Doesn't matter, but beta equal to 2. Okay, so that is there. So you could, what is the use of that? You could hope to study lambda 1 up to lambda n using it. Okay, so that is possible, and it is actually, this matrix is somewhat useful. I would say not very useful, but it is useful to for some questions to study. I mean, yeah, for these questions, one can study it using the matrix. But actually, so I must say that there is a third method, which is what we are going to do, which is that there is a different random matrix, which is, so this is a random matrix A, but that random matrix is not as useful as the one that I am going to tell. So this is the tridiagonal random matrix. That have the same eigenvalue density. This is what we are going to talk about. Joint eigenvalue density of these tridiagonal matrices is going to be beta log gas. Beta log gas is the joint density I said, but this is with, let's say for now, quadratic. It's still for Vx equal to x square, but for any beta, we can find a tridiagonal random matrix which has that joint density. So this turns out to be more useful. So this is what I'm going to say. So in fact, this is somewhat, I mean, this is in the last, mainly this has been developed in the last 20 years. So when I was a student, when I first took a random matrix course, so I used to joke that random matrix course starts with this matrix, this GUE random matrix. Okay, so or even most random matrix lectures in early 2000 used to start like that. So A is an n cross n GUE matrix. So you have a random matrix after all. First, they move to the density of eigenvalues, which happens to be beta equal to 2 quadratic log gas. So the matrix is removed in the first step and you go to the density. And then the beta equal to 2 case, as I said, there is a determinator structure. So from the eigenvalue density, they go to the determinator structure, which means that there is one single function, Kn of xy, called the kernel of the determinator point process, which actually describes everything. So random matrix starts by first removing the matrix, then the randomness, and everything is about studying this kernel. Okay, so that was how it used to be. So this matrix is, of course, it's partly joke. One can use this matrix, GUE matrix, for many things but this tridiagonal matrix is more useful and has more probabilistic meaning, and there is reason why it works better for asymptotics. Okay, so that's what I want to. So this will be the subject of the lectures. Okay. So now let me go to the next page. What are these tridiagonal random matrices? So I have already written it here. So this tridiagonal random matrix is like this. Okay, so this is for every n and beta. So this is going to, so here is a random matrix which is written, and it's tridiagonal. It's symmetric and tridiagonal. Symmetric is clear. So tridiagonal means that diagonal entries and the one above that and below that may be non-zero, but everything else is zero. Okay, so only these AIs and BIs are the non-zero entries. So A1, A2, AN in this particular case, we take to be IID normal 0 with variance 2. And B1, B2, Bn minus 1 have explicit distribution. So they are BI squares have chi-square distribution with certain parameters. Okay, so and they are all independent of each other. By the way, Dima, let me just say that if people ask questions in chat or something, I don't see that. So you can convey that to me. You can stop me and interrupt.
But actually, I think everybody must ask questions, not write. Am I right? Because writing questions is not a good idea.
Okay, so I don't know how you are managing. Yeah, I am happy to be interrupted, but some people may hesitate. If they write in chat, then you can stop and let me know. Because I don't see it. I'm just on, I don't see the Zoom side of it, I think. Yeah.
Okay.
Okay, so this is the tridiagonal random matrix where AKs are normal 0, 2, BK squares are chi-squares with varying parameters. They are not IID, but they are independent. All these entries are independent. That is one of the nice things about this matrix, that all the entries are independent. Okay, I have put a 1 over root beta and scaling outside. Let that be. So these are all independent. Then you get this tridiagonal random matrix. And the statement is that the eigenvalues of this random matrix exactly have the density of the quadratic beta log gas. So in other words, so let me, okay, I put that there. So let me write here. So that was e to the minus beta n summation lambda k square k equals 1 up to n times product of lambda I minus lambda j to the power beta over I less than j. Okay. So this is the, well, there is a normalization constant, which I have not written. So the claim is that this Tn beta eigenvalues have this joint density. The quadratic, okay, sorry, there is a, in this, there is a 1 by 4 actually. So beta n by 4 lambda k square. And so by the way, this beta is completely unimportant. That's just a scaling factor, not important. Because you can just absorb that into the lambda k square. You can scale lambda k by square, lambda k square root beta, then that will go away. But this beta is the absolutely important. You cannot scale it away. This is the whole point. That is what controls the interaction. So the beta, just that it's more convenient. If we put the beta in this also, then some answers come out independent of beta. That's all. So it's actually convenient to take this particular scaling where we also have a beta here. But it is this beta that is important in the interaction term. So the claim is that this is the eigenvalue density of this random matrix. Okay. So we will discuss why.
Excuse me.
Yes.
Can I ask a question?
Yes.
For beta equals 2, does this tridiagonal matrix has something to do with the coefficients of three-term relation for orthogonal polynomials?
It always has, because any tridiagonal matrix, well, this is what is called a Jacobi matrix.
Yeah, exactly.
Every Jacobi matrix has to do with some orthogonal polynomials. We will come to that. But this is a random one. So in some sense, this is a random three-term recurrence actually. So this is a random three-term recurrence. So in some sense, this is a random sequence of orthogonal polynomials. I'll mention that later. So beta equal to 2 is not particularly special in this form. Not that I know
of. Thank you.
Sorry, another question.
Yes.
I see beta in the notation for chi-square random variables. Is it the same beta as
Yes.
in
That
your
in fact, yes, yes. So again, this beta outside here in the matrix is only a matter of scaling. That's not going to change the eigenvalue density in any dramatic way. It will just scale it. So the entire dependence on beta, the real dependence on beta of this matrix comes in the chi-square random variables, the parameters. This cannot be scaled away. It's the same beta. Yes.
and this is multiplication or what? Beta.
Yes, beta
n.
times n minus k. Beta times n minus k. Yes.
Okay.
Yeah, that's correct. Okay. And yeah, all right. Okay. So that is the statement that this eigenvalue density of this random matrix is the beta log gas with quadratic potential. But actually something more is true. So let me say that it will be important. It's not just the eigenvalue density. There is something called the spectral measure. So if you have a symmetric matrix, A n cross n, let's say Hermitian or real symmetric. So let's say Hermitian. These matrices are going to be just real symmetric. So Hermitian matrix, and let's say V is a vector in Cn. So then there is a spectral measure of, the spectral measures of, let's take A to the P, V inner product V. If you take these numbers as P changes, they are the moments of a measure, and that measure is called the spectral measure of A at this vector E, at this vector V. Okay, so that is what the spectral measure of the matrix at this vector is. Well, it is actually something very explicit actually. So there is no mystery in that. So if A is, if A has spectral decomposition, let us say, let me just write mu1, V1, V1 star plus mu n, Vn, Vn star, then what is the spectral measure? The spectral measure of this at a vector V is a measure supported at the eigenvalues. It's always supported at the eigenvalues. Okay, so mu k's are the eigenvalues. So these are only the masses depend on V, and the dependence on the masses is V inner product Vk square. Okay, so Vk is an orthonormal system of eigenvectors for A. So if V is a unit vector, then this is a probability measure because sum of norm VV mod VVk square is 1. So this will be a probability measure for a unit vector. So this is called the spectral measure of A at V. And what I'm saying here is that with this tridiagonal matrix, it's not just the eigenvalues, but the spectral measure at the first coordinate vector. We can tell what is the explicit density. So what is the spectral measure of T at the first coordinate vector? E1 is the vectors 1, 0, 0, dot, dot, dot. So that is there are some weights and some eigenvalues, right? So both are random because this T is random. And the claim is not just the eigenvalue density, but we can work out the explicit density of P as well as lambda. This vector P1, P2, Pn is now a probability vector because we are taking spectral measure at a unit vector. So this is a probability vector. It has an explicit distribution called Dirichlet distribution with these parameters. And this lambda 1, lambda 2, lambda n has this distribution of the quadratic log gas, which is written up here. And these two are in fact independent. The weights of the spectral measure and the eigenvalues are actually independent of each other. So this is a more general statement than just saying that the eigenvalue density is the quadratic log gas. Okay, so this is the more general statement that this tridiagonal matrix has this property. Now, so many questions now. So first of all, why is that so? Where do I get this from? All those questions are there. But first I thought maybe rather than explain why, how do you derive this, I will postpone that and see why this is actually useful. Maybe first we'll discuss how this is useful in some simple properties of the beta log gas can be derived from this random matrix. And I want to show that. And then we will come back and see how this is derived, why this is true. I won't show the full proof, but I will indicate some. I'll say there are interesting things to say about this, because then it also raises the question whether we can do it for general potentials V, or is it only for quadratic potential, etc. So all such questions I will postpone to later. So what I want to show first is that this is actually a useful thing. Okay, so if there are any questions, so that goes into the next thing. So I want to show some of the users already answering some very basic, to a basic sense, basic level. I want to answer some of the questions that I outlined here. What is the distribution of the particles? Where is the maximum? Where is the minimum, etc. Okay, using this tridiagonal matrix. Okay, so if there are no questions, then I go on, first show some uses, and then come back and address how this comes about, why this tridiagonal matrix gives us all this.
Excuse me, maybe just a little clarification. This works for potential which is squared,
yes,
x squared.
so this is for,
only.
Yeah, this is for 1/4 lambda k square as of now. Yeah, so, well, yeah, later I will say that there are a few special cases which are also possible. And even for general V, one can write it. So let me just forecasting what I will do later. There are some special models for those who have seen it. Instead of this is called the GUE, but there are all Hermite ensemble. There are some other special ensembles called Legge ensemble and Jacobi ensemble. For that also, there are random tridiagonal matrices which give this thing. All of them with independent entries. That is what makes this very nice. But when we take it with a general V, we can write a tridiagonal matrix, but it will no longer have independent entries, and that creates a lot of difficulty in its analysis. Okay, so for example, if we take Vx equal to x to the 4, we will see later that AIs and BIs will not be independent, but they will have a sort of Markov structure. So you can think that as you go down here, A1 through AN, or think of A1, B1 as a vector, A1, B1, then you go to A2, B2, then you go to A3, B3, that will have a Markov, that will be a kind of Markov chain. If you take Vx equal to x to the 4, that will be a Markov chain with memory 2, and so on, like that. So and that complicates the analysis a lot. So, but as of now, I stick to this quadratic potential.
Thank you. Got it.
Okay. So any other questions? Otherwise, let me show some uses of this. For example, a very non-trivial theorem in if you use the GUE random matrix. So even say if you want to, this is of course more general because it works for all beta. But even for beta equal to 2, there is one theorem that I want to show you, which is actually quite non-trivial for using the GUE matrix or the direct. Okay, from the direct density, it is doable. I will remark on that later. But from the tridiagonal matrix, it will be very clear. So here is the theorem. Okay, so this is, I have not written the name here. So one can say this is Fiori-Komlos. Okay, there are some accents which I forgot. So, okay, their theorem is more general, but let us say for this, in our context, it is telling us that all the particles of this quadratic beta log gas. So again, we are only talking about this for now, beta n by 4 summation lambda k square times this product. So we are talking only about this density. So the statement is that all the particles are in -2 to 2, more or less, in the sense that you may have to enlarge a little bit depending on n, but -2 minus little of n, 2 plus little of n, with probability going to 1. So what I mean here is that, of course, so there exists some epsilon n, delta n going down to 0, such that the probability that all the -2 minus epsilon n less than equal to the first one, and which is and lambda n is less than equal to 2 plus epsilon n, that probability is greater than equal to 1 minus delta n. Okay, so this is is a statement that most of the particles are especially in, so as a corollary, we see that, strictly speaking, I should write here lambda super n sub 1 and lambda super n sub n, because with n, that entire vector distribution changes. Okay, so the statement as a corollary of that is that lambda n, okay, it's not a corollary yet. Okay, it will come later. So let me just write this. This is not quite a corollary.
Manju,
Yes.
Manju, that is for any positive beta, right?
Yes. Yes. This
Thanks.
is for any beta. This is true. Yes. So that yeah. So this is why this scaling with beta, putting the beta in this exponent also is useful, because this some answers become independent of beta. Otherwise, I would have the beta dependence in the number here.
Okay, thanks.
Okay. So lambda n, the largest one, it actually converges to 2 in probability. Okay, so okay, it is not immediate corollary from here. From here you get an upper bound. We will see later. From what we will do today, it will be a corollary. Okay, so this is telling us this. But how do we say this? And is it not obvious from the original density? Okay, so first let me tell you how this is coming from the tridiagonal random matrix, and then let me say whether it is possible or not to do it from the other methods, namely the original density, or from the GUE random matrix for the beta equal to 2 case. So this proof is actually the first person to do this kind of thing. He did it in a different one, which is slightly more interesting. I will say that later. Is Jack Silverstein. In 1984 or so, he has a paper where he considered what is called a Legge ensemble. There is a more interesting phenomenon, but it's the same proof anyway. Okay, so the idea is very simple. So because the tridiagonal matrix, you remember, what does the tridiagonal matrix have? It has A1, A2, AN on the diagonals, and B1, Bn minus 1 off diagonal, and the same things here below the diagonal, and every other entry is 0. And we are going to scale this whole thing by square root beta n. So this is what I call T beta n, and the eigenvalues of this have the beta log gas density, right? So this was my T beta n, and this eigenvalues of T beta n have the density, and you remember that AK is normal 0, 2, and BK square is chi square with beta times n minus k, and all are independent. So what? I mean, the eigenvalues we know are by this very simple fact that all the eigenvalues, so all the eigenvalues, let's say mod lambda I maximum. Oops, sorry. So the absolute values of the eigenvalues, maximum of that can be bounded by the maximum of the absolute row sum. What are the row sums? Okay, so let me just write here instead of, so, well, sorry. What is the maximum of the row sums? So absolute row sum. So in other words, if you take the kth row, mod AK plus mod BK plus mod BK minus 1. Okay, so this is K 0 less than equal to, sorry, this is K is 1. So for K between 1 and n, so these are the absolute row sums. Okay, B0 is 0. The first row sum will be mod A1 plus mod B1, and the second one is absolute B1 plus absolute A2 plus absolute B2, and so on. So the maximum of this is a very simple fact in linear algebra, that the eigenvalues are bounded by these numbers. But okay, these are not the entries. Sorry, I forgot there is a scaling. So there is a divided by square root beta n. Okay, the whole thing. So which is anyway bounded by, I can make it easily. So less than equal to, let us take maximum of ak over square root beta n over k plus maximum over k of bk doesn't need an absolute value, bk over square root beta n, but there are two of them, so maybe I put a 2 here. It's clear, right? So bk and bk minus 1, so I bound them both by the maximum of this bk, so I get this. The thing is, so now these are very explicit distributions and we understand it completely. So maximum of n IID Gaussians, we know how this is. This is small and this is actually close to 2 because of the factor of 2. Okay, so this is what I'll just explain. It's clear, but if you haven't seen this kind of calculation, maybe I just explain, it doesn't take long. So see, maximum of n Gaussians, each Gaussian is of unit order. How big is the maximum of n Gaussians? So maximum of n Gaussians, so probability that maximum of k, ak, absolute ak, is more than, let us say, t times square root beta n. How big is that? So by the union bound, it is bounded by n times probability that one of them beats t root beta n. And for that, we can write a bound something like e to the minus t square beta n over 2. Okay. So this is a simple bound that we can write. The tail bound of the, I have used the tail bound for the Gaussian distribution, which is also just the Gaussian density is roughly a bound for the Gaussian tail. So this you see, so which says that if t is even something as large as, which is small, if t is somewhat bigger than square root log n over square root n, right? Because if you have square root log n by square root n, you square it. Well, okay, let's put a, okay, no, I don't mean that constant explicitly. So let's say a much bigger than square root log n, let's say. A large constant times square root log n, suppose. Let's say here we have a large constant. So then that you see that exponent will, t squared times n will have a large constant times log n, which will bring a 1 over n to some power. So this will be going to 0. So this will be fine. So this t cannot be much larger than this. So this whole thing is small. By that I mean as small as this. Something like square root log n over square root n. That's all. And what about bk's? Bk square is chi square. Beta times n minus k. Of all of them, the biggest one is b1 square, right? So kind of, let's say this is in some sense smaller than, so let us for a moment just take that it is smaller than chi square beta n. The largest of these is when k is 0, okay. And k is 1, but so these are all in some sense smaller than chi square beta n. And what we know about chi square beta n is that if you take chi square beta n, at least for integer parameters beta n, you know that, let's just write chi square. So it's very basic probability that chi square nu, it has mean nu, and if you divide by square root nu, then it converges to some normal with mean 0 and variance half or 1 or 2, I forget, maybe something like this. Okay, so this is true. But actually, maybe one can write this one. So from this, you also see that if you don't take the square, but the chi itself, that is square root of the chi square variable, that is very close to square root of nu with unit standard deviation. So this converges in distribution to normal 0 something, I don't remember, 2 or half or something like that. So with, here you don't need a scaling. Okay, so our b's are like this, square roots of chi squares. Because of that, if you had, so what we are looking at is maximum of bk over square root beta n. If all of them had chi parameter, sorry, this is for some reason jumping. Yeah. So if we had maximum, if we had bk, we are taking bk over square root beta n. If all of them had square root beta n as the parameter, then what you would see is that chi nu over chi nu is basically square root beta n plus a Gaussian, right? So chi nu over square root nu would look like 1 plus xi, where xi is a normal random variable. So when you look at maximum of that, basically it would look like this. So you would get 1 plus some log n over square root log n over square root n. Actually, it's better because bk's have decreasing parameters. But from this, you can see that this is going to, no, this will not work because this would give us a, no, actually this is fine. So this will tell us that it is smaller than something like the little of n is basically some term like this. Because bk over square root beta n can be bounded by 1 plus a kind of Gaussian, and so you have max of n Gaussians that is again bounded. So with all this, this is I just gave an argument, maybe more detailed than needed, that this quantity that we had here, so that this quantity that I had here, so this is actually not going to be much larger than 2. So that basically tells me that that quantity is it's something, it tells us probably something like less than equal to 2 plus maybe square root log n over square root n with high probability. So if you put a large constant here, a large constant, maybe you will get what probability 1 minus n to the minus some another constant which will depend on that constant. Something like this is what you will get from this argument. This is not optimal, by the way, but this shows what I was saying, that all these particles are actually in minus 2 to 2 with high probability. Okay, so that completes this proof. It's very simple, very elementary, just basic linear algebra, one linear algebra fact and very basic probability facts, because we understand Gaussian and chi-square random variables. So any questions or clarifications about this before I move on to the next thing? This was the first use I wanted to show of the tridiagonal random matrix.
Is optimal epsilon n known here?
Yes, yes. So the thing is, yeah, we will come to that later. Again, we will deduce from here the optimal epsilon n is actually, so this is a very important fact, that optimal is n to the minus 2/3. We will see later, we will derive this in fact using the tridiagonal matrix, but that is actually n to the minus 2/3.
Excuse
So
me,
we
does it
have
this minus 2/3, does it have something to do with the Airy kernel also? Because that's the asymptotics for.
Yes. But A is the special case. When beta is 2, you get this A process, or beta equals 1, beta equals 2. But this is more generally for any beta, this is 2. So this, I mean, this kind of generalizes those A processes. So they are after, because originally what was called A process. So this is, so we will not be talking about them, but these some special functions called A functions, and there are some processes defined in terms of those. So this was done specially for beta equals 2 and so on. And now that it was done for general beta using this tridiagonal matrix, those processes are called A beta processes. But they don't have anything, I mean, I don't think there is a very specific special functions for the A beta process that are like for beta equals 2 and so on. But it makes sense to call it A beta process.
Thank you.
Hello, sir. Hello.
Yeah, yes.
The inequality you wrote about the two chi-squares, is that stochastic domination you were saying?
Yes. So this is a stochastic domination. I mean, chi-square with beta n is a sum of beta n many squares of Gaussians, and this is a sum of, when these are integers, beta times n minus k squares of Gaussians. So it is clearly larger than that. Okay, it's also true when non-integer parameters, but yes, stochastically smaller.
Okay, thanks.
So in other words, all these tails and probability bounds are valid. Whatever upper bound I get for this, the same upper bound is true for bk square with the same, better probability bounds. That's all. Okay, so any other questions? If not, okay, so I forgot. So before moving on to the next, I also promised to say, can we do this by the original density? Okay, so you say, oh, you are saying that there's this simple approach which tells you something about this process, but could you not have done it directly from the joint density here? I mean, the original beta log gas density, or this one, or from this, in the special case, beta equal to 2 from this GUE random matrix. Could we or could we not do these things? Now, the beta equal to 2 matrix, if you take that random matrix, GUE random matrix, that is sort of what Furedi and Komlos did. It is quite complicated, but the advantage is they also work with general distributions, not just GUE. In other words, in GUE random matrix, I had Gaussian distribution, Gaussian random variables, but they consider what are called general Wigner matrices, where you have random symmetric matrix with IID random variables in the upper triangular part from a general distribution with some assumptions on moments. So their method works for that also, but you have to study very high powers of the traces of high powers of that matrix, and quite a bit of combinatorics is there. This is, I can say without any, there is no lie here to say that this proof is simpler. Okay, but this doesn't work for the general Wigner matrix, of course. But what about the original density anyway? So can we argue it from here? Actually, this is one question where, yes, the thing is, this is possible to do it from here. There is something that is possible here, which is actually something more. Maybe I see, but although it's not the subject matter of my lectures, let me just indicate here. Can we argue this directly from the density? Can we do this directly from the joint density? It's sort of possible. The thing is, the joint density, if you remember, looks like this. I'm writing it again. So I'll write it in beta n square times that energy that was there. What was the energy? So remember, the energy term had 1 over n v of lambda k and 1 over n square this one. So one can write it like this. So one can write it. So let's consider this measure ln, which puts mass 1 over n at all the points lambda case. Okay, I may say eigenvalues, but I mean this beta log gas particles. So look at this probability, random probability measure, Ln. We'll call it empirical measure, empirical spectral measure, whatever. So that the first term can be written as V of x d ln of x. Okay, so why it is, you see that first term is 1 over n summation v lambda k. That's the average of v with respect to this measure ln. So it is just integral of v with respect to this. Now, what is the second term? It is sum of I less than j log mod lambda I minus lambda j over n square. So let's make it 2 times and write for all I not equal to j, or half of for all I not equal to j. So I'll get here. Okay, actually, maybe I should have put a 2 here. Okay, I don't remember. Maybe I should have put a 2 here. It's not so important. So, by the way, I have put 2 references in the abstract. One can look at it. I have not made separate notes or anything. But anything, all the mistakes that I make here, some of them are corrected there. Okay, and all the mistakes that are there, you can find. So this second one can be written as a double integral of log mod x minus y with respect to ln of x d ln of y. Okay, almost. Well, if you do that, you will get a factor of half. The half comes from the fact that here I had 1 over n square and sum over only I less than j. I make it I not equal to j. So then it almost looks like this, except that x equal to y terms I have to worry about. So I have to introduce here a term indicator x not equal to y. Okay, so this is how that density looks. Well, okay, not exactly. That's not the full density. This is without the normalization constant. So if you put the normalization constant also, then there will be some another minus some Cn beta. Okay, with the normalization constant, it will look like this. Yeah, okay, don't worry about the normalization constant. But what this suggests intuitively, and I will make a statement. I don't know if everyone is familiar with large deviations or not, but I will nevertheless say it. If you do not know anything about large deviations, just ignore whatever I'm saying, because I won't be able to explain these terms. It will take too much time away. So intuitively, what this says, I will explain a little bit. So that LNs, these empirical measures, these are random things which satisfy a large deviation principle in the space of probabilities measures. So let's take the space of probability measures on the real line. In that space, ln satisfy a large deviation principle with rate n squared. The n squared comes from the fact that here it's exponential in n squared, and the large deviation rate function, which is what is called good rate function in this literature of large deviation. There is a standard definition of good rate function. What is that rate function? It is a function on the space of probability measures. What this says is that it is this function that this is the double, it is integral. You take whatever is here and put mu in place of ln. That's what that is. Vx d mu of x minus 1/2 double integral log of mod x minus y d mu of x d mu of y. Okay, so if this doesn't exist, okay, whenever this exists, otherwise it will be what is it? It will be infinity if this integral doesn't exist. Okay, so this is exactly the term here. What is underlined here is exactly the same for ln. It's almost like I of ln, except for this irritating term indicator x not equal to y. Except for that, it looks like, in fact, for ln, this I of mu will be infinity. If you take the literal definition, because ln is a discrete measure, x equal to y terms will contribute, and that will give me a plus infinity. But if you include that indicator x not equal to y term, this looks very much like this, and ln satisfy large deviation principle with this rate n squared and with this rate function. So what that means, so this is the only explanation I will give for what this statement means. Here we have this space P of R, the space of all probability measures on the real line, and this ln is a random measure. Okay, what happens is that what is the probability that ln belongs to a neighborhood of a probability measure? I give you a probability measure mu, and I ask what's the chance ln belongs to a small neighborhood of that measure. Basically, you should think of that as that probability as being e to the minus beta n square, the probability that ln falls here. That probability is approximately like beta n squared I of mu. That is the intuitive meaning of this large deviation principle, that the probability your ln is close to mu is like e to the minus beta n squared I of mu. Okay, so well, actually I made a small error here. So there is a small constant to subtract here. The constant is such that C is such that infimum of I of mu is actually 0. Okay, so this I, it turns out, has a lower bound, and you lift it up without that C, that it had a lower bound, you lift it up so that its infimum is 0. And in fact, there exists a unique mu sub v such that the I of mu v is exactly this infimum of I of mu. Okay, so that is that's a statement I am making. Okay, this is coming from this is, well, you need some conditions on V for this to happen. If V goes like polynomial, then it is okay. So it is true. This is called the equilibrium measure. This is called weighted potential theory with logarithmic potential. But the fact is there is a unique minimizer for this thing. So in other words, there is that mu V. So what is that mu? If you take a neighborhood of that mu V, the exponent is 0. I of mu V is 0. So only around that point, that is a unique probability measure. Only around that, the probability does not decay. So in other words, Ln, everywhere else, the probability decays extremely fast. Like whatever be I of mu, it will be some positive number. It will, whereas here it is 0. So here the probability is something, whereas everywhere else it is e to the minus beta n squared. Like, therefore, Ln is very, very highly likely to be in a neighborhood of this mu sub v. That is the what you get from this large deviation principle. So what does this have to do with this mu sub v? This mu sub v is basically, okay, so if you ask where are the particles, the support of mu v you would expect is what tells you where the particles are. And the support of mu sub v will be this minus 2 to 2 in this quadratic case. In the quadratic case, if you work out, okay, in the quadratic case, when Vx is x square, so for Vx equal to x square by 4 or whatever that is, mu v turns out to be this specific thing that I'm going to introduce later called the Wigner Semicircle Law, which is supported on minus 2 to 2. So in this sense, the large deviation principle also tells you that the particles are in minus 2 to 2. Okay, strictly speaking, it's not the large deviation itself. You have to slightly go into the proof of it, because large deviation, the statement is an asymptotic statement. It doesn't tell you kind of finite bounds, no quantitative bounds like this are immediate from the statement of large deviation. But if you go into the proof, you need to analyze a bit and you will get such statements that all the particles are in minus 2 to 2. Not only that, you also get this other statement that the particles are distributed according to this mu sub v. So this Ln, which is how the histogram of these particles looks like the measure mu sub v with very high probability. Okay, that all comes from the joint density. Okay, so in that sense, yes, for this particular problem, one could also have worked without the tridiagonal random matrix. But well, it is a little more technical, but also results are more. But tridiagonal matrix gives you an elegant, nice elementary way to get this result. Okay, so that finishes my discussion of this first use of the tridiagonal random matrix. Okay, it is useful, though in this case not quite indispensable. It could have been done by other methods. Okay, now if there are no other questions, then I will move on to the next use. So I will have to also come back to, okay, maybe I'll get to the next use and then come back to how, or maybe that will be in the next lecture, how this tridiagonal matrix comes about. Okay. Okay, any questions or anything so far?
Maybe I have a question. My sound disappeared for a while, so I missed about these tridiagonal techniques, but you proved that it is not supported on minus 2, 2. It is inside minus 2, 2. So this corollary that the maximum eigenvalue goes to 2, actually we didn't prove, right?
No, not yet, not yet. Yes, exactly. I wrote corollary, but then I said, no, it only, this so far only gives me an upper bound. It tells me that sometimes lambda n bigger than 2 plus epsilon goes to 0. Yeah, this will follow from the next thing that I do.
Okay. Thanks.
The lower bound will come from what I do next. Okay. Okay. So I'll next go to this one. It is one of the first theorems usually taught in any random matrix course. That, okay, it depends on which model you start with, often with the GUE or some Wigner random matrix. And what one says is that, again, I bring this empirical measure, which is this Ln. Okay, so this Ln. So again, we are back to this quadratic beta log gas. So the same thing. So it's 8 o'clock. Okay, so again, so e to the minus beta n over 4 summation lambda k square and product lambda I minus lambda j raised to the power beta. Okay, so this, so again, we look at Ln, which is the empirical distribution of the particles, put mass 1 over n at all of them. So this is the histogram, and Ln bar is the expected empirical. So this is the sometimes called EESD, expected empirical spectral distribution, if you want. So it is a convex combination of measures. So it is another measure. So Ln is a random measure. Ln bar is a non-random probability measure. Okay, but nevertheless, both of them converge to this distribution called the Wigner semicircle distribution, which looks like this. So the density looks something like this. Okay, this is a very bad picture of Wigner semicircle law. So it is symmetric about 2, and it looks like this. So the density is square root of 4 minus x square. It vanishes at the two endpoints like a square root function, and Ln and Ln bar, they both converge to this. So Ln bar converges to this is clear what it means. It means in the sense of convergence in distributions, Ln bar is a probability measure. So in Levy distance, it gets close to, or maybe in some stronger forms of Levy distance, but definitely in Levy distance, it gets close to this semicircle distribution. Ln is a random measure. So what do I mean by Ln converges to that? So it just means that probability that, or if you take the Levy distance between Ln and sigma, probability that is bigger than epsilon goes to 0. That is what this is. Okay, so the Levy distance between Ln and sigma goes to 0. So in other words, one should say Ln converges to sigma in probability. Okay, so that's what this statement is. So this is a statement, and so as I said just a moment ago, in this, if you go through this method but directly from the density, you will end up with this weighted potential problem. You have to minimize this energy, and then you get the semicircle. So semicircle will appear as the unique minimizer of this energy function when you take Vx to be x square. It will appear in a very different way from the tridiagonal random matrix. Okay, so that's what I want to now show. How do you get this from the tridiagonal random matrix? But like rather than jump to the empirical distribution, we had another distribution. So this empirical distribution, how is it related to the spectral density? So remember we had this mu E1 Tn, or more generally mu E2 Tn, or you can take it at any vector. You remember this measure, right? So let me just, I can't write it again. So let me go back here. Yeah, the spectral measure of T at any vector V is that vector whose pth moment is a to the p V inner product V, or in other words, the density of the spectral measure is just supported on the eigenvalues with density, masses, which are the how much V projects onto Vk, the square norms of the projection of V onto Vk. Those are the weights of this measure. Okay, so we can consider mu t E1 or mu t E2, etc. What one can see is that basically if you take any orthonormal basis, so let's for example take the orthonormal basis of coordinate vectors. Actually it works for any orthonormal basis, but if you average those things, so these are n probability measures. So let me take a convex combination, so I get another probability measure. This is nothing but Ln actually. It is very easy to see that, because when I take mu t and E1, what I get is so here this will have the weight at lambda k. So delta lambda k will come with the weight, the kth eigenvector, the first coordinate squared. That's what will be the weight of that in this measure. In this one, the weight of that same thing will be Vk inner product E2 square. That will be the mass at lambda k, and so on up to this one, which will have Vn inner product, Vk inner product En square. So they sum to 1, right? So when you average this out, you just get 1 over n mass at each of the. So when you add them and divide by n, you get mass 1 over n at each lambda k. So that's what Ln is. So Ln is the average of these individual spectral measures. So rather than jump directly to Ln, let's look at what happens to mu Tn E1. So let's look at mu Tn E1, for example. What happens to that as n goes to infinity? So mu Tn E1, if you see the moment x to the p by definition is Tn to the power p E1 inner product E1. So what does that look like? I will make some approximations. So we have to use this tridiagonal matrix. So let's just write that here. So let me show the tridiagonal matrix here. So what was the tridiagonal matrix? It had this A1, B1, AN and B1, B2, Bn minus 1. AKs are normal 0, 2. BK squares are BKs are chi random variables with this. So, and I'm going to divide by square root beta n. So what I say is that when I divide the Gaussian is of unit order. When I divide by square root beta n, it will be very small. The diagonal entries are very small. What about B1, B2, Bk? So Bk is approximately by what we did earlier. Chi nu random variable behaves like square root nu. So Bk for all purposes is like square root of beta times n minus k. So when you divide by this, it looks approximately like square root of n minus k or square root of n. So in other words, what I am going to say is that I will make an approximation here and I will just say that Tn is approximately like this matrix, which will simplify my life, that I on the diagonals I just have zeros because I have ak over square root beta n. On the off diagonal, b1 is square root beta times n minus 1. That's what it is like. And if we divide by square root beta n, so it looks like square root of 1 minus 1 by n. Here I have something like square root of 1 minus 2 over n, and so on, square root of 1 minus 3 over n, and so on up to, in the end, we have square root of 1 over n. And the same things on the bottom also. Okay, so I will make this approximation. So the point is, of course, you have to strictly argue that in the calculations that I'm going to do, you can carry through these approximations. It's not hard, but it's maybe not worth explaining here. So if you do that, it simplifies a great deal. What will be Tn to the p E1 E1? This is just the 1 entry of Tn raised to the power p, right? That's what I'm talking about. But you see, so when you take that, you have to, well, so this can be written as T of 1, I can I2, T of I2, I3, and so on up to T of IP, I1, IP, and then 1. I have to start at 1 and come back to 1, and I2, IP can be any numbers between 1 and n. But because it is tridiagonal, ik plus 1 minus ik should be at plus or minus 1. Also zeros in the diagonal. So if ik plus 1 is ik, I get a zero contribution from the diagonal. So that also I can exclude. So this looks like a walk on integers. You have to go each time. I2 will be only 2. I2 has only one choice. One, you start at 1. I2 has to be 2. But I3 can be either 1 or 3 and so on. Finally, from IP again has to be 2 and then you come to 1. So we have to add up these numbers. So what will that look like? Now, how many such walks are there? But we also have to have this, nothing can go below 0, right? So how many, and what are these weights like? You are taking for fixed P. So we are working with a fixed P. Suppose your P is fixed. Oops. If you fix P, let's say P is 10, then you are going to use only the top 10 entries, some 10 entries in this. So they are all going to look like 1 approximately. All these entries in the beginning, they are going to look like 1. So these weights are actually 1. Okay, T1, I2, Ti2, I3, Tip, I1. When P is fixed, then n goes to infinity. All those weights are 1. So it's just a question of number of walks on Z from, let's say, 0 to 0 in P steps, but not on Z, but on Z plus. So I cannot go to the negative side. Number of walks on Z plus from 0 to 0. How many is the number? This is a well-known combinatorial problem. The answer is it's the Catalan number. So it is actually depends on P. If P is odd, then there is no such walk. Okay. So this number will be 2Q choose Q. So if I put no restriction, how many walks are there from 0 to 0 in 2Q steps, then I get this. But if I have the condition that it has to stay on the positive side and you start at the origin, then this number is 1 over Q plus 1, this, if P equal to 2Q. And it is 0 if P is odd. Okay, these are the Catalan numbers. And in fact, that number is same as x to the P d sigma of x. That's a direct calculation. If you take this sigma, which is this density, and calculate x to the P against that, you get a beta integral, which you can easily do. And then x to the P d sigma of x, from symmetry it is clear odd moments are 0. For even moments, you get this Catalan number. Therefore, the moments of mu T and E1 are converging to moments of this sigma, from which it follows that mu E1 Tn converges to sigma. Okay, so that's what happens. So this shows that the first spectral measure converges to the semicircle distribution. So if I can show all these mu E2 Tn, mu E2 Tn, all these converge to sigma, then you can kind of believe that the average will also converge to the same thing. Like this is false. Okay, this is completely false. The reason it comes out is actually quite different. It's a bit funny that this comes out like this, but now let us take, suppose I take some, it is a good exercise to do, calculate mu Tn EP for fixed some E, let's say L. L is fixed. So calculate the second, what happens to mu Tn E2. Okay, you don't get sigma, you get something else. It's actually, you get different ones. For L fixed, let me leave it as exercise, but let me take somewhere deep inside. Mu Tn, let me take it at Ek, where K is, depending on N, K is N times some U, where U is between 0 and 1. So in other words, I go deep into the matrix. So I am not looking at the beginning, but I'm going somewhere a fraction into the matrix. K is N times U, and I want to see what happens to the spectral measure here. The same logic works. We use the method of moments. Okay. So the point is, this method of moments works with matrix. It's a well-known thing in random matrices, but it's much easier in tridiagonal matrices because the combinatorics is so much simpler. So what happens to x to the P d mu Ek of Tn of x? What does that look like? Again, this is nothing but Tn to the P k comma k. Sorry, no, what am I written? No, this is just Tn to the P k comma k, nothing more. There is no sum. And what does that look like? Well, again, it is just the sum over all trajectories. I get T of I1 to I2, Ti2 to I3, up to T of IP to I1, where again I1 up to IP are between 1 and n, and I can say Ik plus 1 minus Ik is plus or minus 1 because of this condition. I mean, I'm using this simplified matrix, where all randomness has been removed anyway. So this is they
Manju,
Yeah.
I'm sorry, maybe it's better to stop to continue
okay.
tomorrow because the participants need some rest before the next
Oh,
lecture.
is it time? Okay, sorry. Is it time? Okay. Yeah, so then maybe I will stop right here and take it up from here. That's okay. So I was going to say what measure comes out here. So for those who want to do it for themselves, maybe they can try to show that this converges to the arc sign distribution. But I will, like Dima says, let me continue next time, tomorrow, that is.
Okay, thank you very much, Manju. Are there any questions to him? Okay, I have one small question. Who and when first found this nice connection between log gas, beta log gas, and tridiagonal matrices?
That's a good question. So I mean, I would have, I was planning to tell it when I say how this comes. So this is the history is very quickly is this, that it was done by Trotter in 1984, I think, or 83, sometime like that. What he did was very specific for beta equals 2 and 1. Well, what he did not actually he was not looking at the beta log gas. So what he was looking at, so GUE or GOE matrices. Okay, for those who know, GUE I defined, GOE is something similar, but with real Gaussians. So he was looking at the GUE and GOE random matrices, and then their density was known to be exactly this one with beta equal to 2 and 1 for G. And so what he did was he got the tridiagonal random matrix by working on the GUE random matrix. He reduced by similarity transformations to a tridiagonal matrix here. And he could do the same for GOE, and consequently he found this simple proof we are giving of Wigner Semicircle Law. That is what he did. And soon after that, Jack Silverstein used that to show the other application that I showed, that the eigenvalues are where they are supported. He showed that. But the idea that you can make this general, so at that level, so that at the level of full matrices, there is nothing that works for general beta. For beta equals 1 and 2, you have these. For general beta, there isn't. But when you go to the tridiagonal, you can generalize by generalizing the chi-square parameter. That is due to Johanna Dimitriou and Alan Edelman. I think it is approximately 2000. They were the ones who did it for general beta. The idea that you can put a general beta. And then they did it for this Hermite and Laguerre case, and later it was done for Jacobi by Edelman and Sutton and Kilip and Nenchu and so on. Okay, that's the answer to the.
Oh, okay, thanks. Thank you very much again. And okay, and we are meeting in 12 minutes for the next lecture. And Manju, please make me a host again, please.
Oh, okay, sure.
Thanks.
So, okay, so. Okay, Dima, now you are host.
Okay, thank you very much.
Okay, thanks.
Manju, are you still here? Okay, yeah, probably not.
I am here. Sorry, I was
here. Yeah, I was just wondering. There's one little question. Is there any extension of this connection between tridiagonal matrices and processes for infinite processes with infinite number of points, like Airy, sign process, Bessel, what?
Well, yes, in the sense that is what I will mention, not do in detail later. The thing is, we can take limits of these, and we get stochastic operators. So this tridiagonal matrix, this is one of the advantages of this tridiagonal matrix, that this is a second order difference operator. In a certain scaling limit, one can get a second order random differential operator. That is that, and one can describe this Airy process as the eigenvalues. One can show that has a discrete spectrum and the A process is just the eigenvalues of that random second order operator.
Okay. Yeah. Thanks. And where can I find some more information about it?
So this is so I have put reference to 2 notes in the abstract. So the work itself, it was done. I mean, the suggestions were made by Edelman, but all this most of it was done by Brian Ryder, Balint Virag, and Jose Ramirez. There is a paper where they worked out this stochastic A operator. And then there are many other papers where it is taken to other Legge ensembles and many other things. And also bulk. Also, one can do something in the bulk, which is more complicated.
For sign? For
sign process? For sign kernel process.
Yeah.
Yeah. So it is somehow the edge is easier. The bulk is kind of more complicated in some way.
Well, usually it's the other way around, but okay.
There is a description in terms of stochastic differential equations. The description is not more complicated, but the convergence is somewhat more involved. It's straightforward.
Okay. Thank you very much. Very nice lecture. Very nice talk.